Hello, my name is Clare Sudbery. I'm a technical coach, and I am here today with Andreas Zeller, who's going to tell us about the Debugging Book. So, Andreas, would you like to introduce yourself?
Yeah, I am Andreas Zeller. I'm a software researcher at the CISPA Helmholtz Center for Information Security. I'm what you would call a senior researcher. In the US, I would be a full professor with plenty of experience in testing and debugging software, both testing and debugging software myself, as well as building tools and techniques that help testing and debugging software.
Marvelous. And how long have you worked there?
Well, I think the first time I was debugging a program was at the age of 18, and I spent a long night debugging it until it worked. And that's now something like 41 years ago.
Wow. And what language was that you were using at the age of 18?
Oh, that actually was a programmable Casio calculator of all things.
Wow. Fantastic. What were you getting it to do? What was the program? Can you remember even?
I think I wanted to get it to play some game, something like Monopoly or something, and there was something wrong with the alignment of the individual fields. I was programming games for that calculator and selling them to make a bit of extra money.
Fantastic. I love that. And then you ended up being a software engineer. Was that a quick journey?
Well, it was a bit complicated. First, I found that I had a passion for programming and for developing. So I studied computer science, and I was pretty good at that. After I finished my studies, I was offered a position to do a PhD, and I thought that, well, researching software is fun. And at the time, I thought, well, there's so many things that can still be improved, so let's do some research in the area. And I did then some work in improving version control systems, which at the time were very new. Yeah. Today, of course, they're common practice. Thanks, among others, to my great community who's been working on that. Mm-hmm. And while I was building systems, I also found that, well, we still need to do much more as it comes to helping developers in testing and debugging their software. So after I did my PhD, I continued an academic career, which would give me all the freedom I wanted for this particular purpose.
Amazing. And here we are now. You've written this book, the Debugging Book, but it's not a book in the traditional sense. It's an unusual format. How did you come up with the idea of, and do you want to describe a bit how the book is sort of packaged? I'm not quite sure what adjective to use, but do you want to describe the format of the book and how did you come up with that idea?
Yes. So traditionally in academics and in publishing, a book is a collection of pages. There you go. Mm-hmm. Whether these would be printed or come as a PDF these days for download, or whether you look at them on your reader, it's a text that is to be written like, say, a novel would be written from beginning to end, or maybe it's a reference where you can look things up. But you see, this is also the standard in academic publishing. We publish papers, and we call them papers because, well, they come in paper form. But, you know, when we are doing our research, when we're building things, we typically build something that is not just made to be described in words, but it's actually something that is to be used, that is to be dealt with, that is to be executed. So most of our artifacts in research, in my field, actually come in the form of programs that you actually write, and then you run them, and then you see that they work or they don't work, or you analyze existing programs. But there's always some artifact behind it that allows you to, that you can execute and where you can try things out for yourself. And the same goes if you're building a new tool, for instance. Say I build a new debugging tool because I have this new idea for what could help during debugging. And so I implement something, and then I see that it works. But then magic happens, the tool disappears, and all I do is I write a paper about it. That's And of course, I can make the tool downloadable somewhere, but the two things are very separated classically. Okay, and the idea is actually to bring these both concepts, the concept of a book and the concept of executable program, to put these together in one single format. That is, while you already have the book on your screen, because most of us, well, in particular in the academic world, are reading things on screen and on readers anyway. While you have these things on your screen already, why not just go and interact with them directly? Trying out whether something works, trying out what the effect of something is. And when I, as an author, I give an example, how about you do this? How about you do that? The idea is to make this available immediately to the reader, such that the reader can directly toy with it and experiment themselves, such that figuring out how a particular thing might work. And this is the key of the books I'm doing these days, notably the debugging book. The idea is that you're reading things on the screen, you're reading about a particular technique, but you also follow the steps of how to build this, what comes out at the end, and you can toy with it directly, interactively on your screen and try out how a particular technique works, try out other parameters, variants. Hey, you can even add your own code to the whole thing, and then make your own experiments. So it's much more than a book in the traditional sense. It is actually a playground where you can do your own experiments, change things at your liking. Hey, you can even go and change the writing if you like. So, except that your changes stay with yourself and they do propagate to the book themselves.
Yeah. And so what users, or rather users, what they get is a combination of short video clips and printed word, which is navigatable via a website. So you're clicking through to get from one chapter to the next. And also these Jupyter notebooks. So you're making the code available. I mean, there's a GitHub repo where you can browse the code as you would any other code base. But there are also these Jupyter notebooks that allow people to interact with the code. Do you want to talk a little bit about that technology?
Jupyter Notebooks is a technology that allows you to combine code and text to your liking, as well as the results of the code that you execute. It is mostly used in fields like data science, where you go and analyze some big chunk of data and you want to see the results of your analysis, such as plots or drawings. You want to see these immediately. So what you do there is you write a piece of code that goes, okay, I want to load this data set and now I want to plot this particular data set. Now I want to do a prediction. And this allows you to interact with the data as you like. The nice thing is it also allows you to add text such that you can actually explain what you're doing. So this is helpful because if you want to share your notebook later on, then you can actually have text that explains the individual steps that you're doing.
Yes.
And the text comes in a very rich format. That is, it's not just what you would have in a program like typewriter text.
Yeah.
But you can actually add formulas to it. You can include images. You can do anything that a professionally typeset book would actually allow you to do.
Wonderful.
So you can also have tables and formulas and images and figures and whatnot.
Yes.
Not everybody uses this. Notably, if you're a data scientist and just want to get to the heart of some data, you don't care about this. But if you want to share your material with others, this is what you do.
Yes.
And these Jupyter notebooks, as I found, are also great tools for authoring in the style that I do.
Yes.
Because there I can take the text fields and then put in what you would normally put in a regular book. So you explain a particular technique, you give the references, this is how it works, and so on and so on. And then come short pieces of code that actually implement these individual techniques.
Yes.
So in step by step, I can then show the reader, okay, first general idea, this is what we plan to do today. Here's the general idea. And then let's go step by step. And while I'm formulating my thoughts, let's do this step, let's do that step. I can illustrate this immediately with code that implements the whole thing. So this means that in contrast to a regular book that shows how a general technique works, I can illustrate each of these steps with actually executable code that readers can try out themselves.
Yes.
And on the other hand, compared to just regular code, program code, this is normally just a long bunch of instructions that are typically not very well documented, but they work. That's the good news. So in contrast to that, I do have plenty of documentation that illustrates the individual steps. So readers can use the program code to better understand the meaning of the words that precede it, and they can use the words that precede it to better understand what the program is doing. And
wonderful.
From a pedagogical perspective, this is of course a nice combination because I can be both casual in my natural language text, but I can also be very precise and formal. That's what the program code is doing because, well, the program code is the ultimate authority on what will actually be happening in the program.
Yes. So I've just realized that we've been talking about how the format of the book, and yet we haven't really talked about what the book is about. I think people can guess because it's called The Debugging Book. But you want to talk a little bit about what the book is about, what it is that you want readers to learn by reading and interacting with the book.
Yes, of course. So all of this so far was the how, but not necessarily the why. Mm-hmm. Okay, so debugging is the act of figuring out why your program fails and fixing the program accordingly. So you have a program and the program crashes or it does the wrong thing. There you go, boom, and then you realize you must fix the whole thing. And for a programmer, these can be very challenging situations because, well, you first have to find out where the bug is before you can fix it. And if you think about that, programs can easily have thousands to even millions lines of code. Somewhere, something is wrong in there. It might be your code. It might be the code of someone else. And you have to figure out, well, where could something be wrong in here? So all of a sudden, you change the perspective. First, as a programmer, you're the creator of things. There you go. You build things and they run. And now all of a sudden, you're a detective. You have to figure out what went wrong.
Yeah.
And often, it is even your own code that is wrong.
Yeah.
Which means that you are in a situation where you're in a situation where you are both the detective as well as the murderer, as one puts it.
Yes.
So, meaning that you have done something wrong, but you don't know what and why and where. You just know that it was you. Yeah. Okay, but and now you have to figure out what actually happened, what actually did you do wrong. And for many programmers, this is difficult because they have to carefully then revisit their assumptions on how the code should work because, well, one of these assumptions must be wrong because otherwise it would work.
Yes.
And that's not always difficult. On the other hand, you also, well, you cannot simply assume that everything is wrong because something must be right. Otherwise, you would be searching forever. So figuring out how to best choose and how to best search in your code, where to go for, this is a hard task. Mm-hmm. And now and since searching for the cause of the bug is something that can take hours, days, weeks, sometimes even. Okay, so if you have somebody who is sitting in front of their code until well after midnight, that is typically because they are still debugging something, and they are looking into. They have a number of hypotheses on what might go wrong. They have made a number of checks. Is this hypothesis true? Is it this? Is it that? Like a detective, for instance. Okay, again, we are investigating a murder case here. But many programmers and then simply keep things in their head, and they're super concentrated, and you cannot disturb them under no circumstances, because otherwise they would lose everything they've built up in their head. And for the same reason, they cannot stop. Okay.
Yeah.
And that's something I also experienced as a younger programmer. I would debug things until 3 a.m., 4 a.m. in the morning, until it would finally come back victorious, and then, I found the bug. That's cool. But the nice thing is that there's a number of techniques that can very much help you in guiding your search and in figuring out where the bug is. Mm-hmm. And these techniques that help you debugging, these are called automated debugging techniques. That is, they help you finding out where the bug is and what the cause is. These are the techniques which I illustrate in this book. Yes. And as I said, I don't just illustrate them, I actually implement them. So with the techniques that are built in the book, you can actually debug your own programs just as well.
Yes. So let's talk a little bit about the detail of that. How about we start by talking about interactive debuggers, which I know is a topic that's very central to the book. Do you want to talk a little bit about that?
Yeah, interactive debuggers is the standard technique that programmers use these days in order to figure out what is going on in the program. Mm-hmm. See, when you're just reading the code is how the program tells you how the program should work in the abstract. Yeah. That is how it should generally work. And that's okay. Many people are able to spot bugs in there just by reasoning about the program. Yeah. But if your program interacts with lots and lots of interfaces which you cannot fully trust and where you cannot read the code, so whatever you're doing, some call into some library that comes from a third party, you typically don't want to debug this as well. You don't want to know what's going on, but still the bug might be in there, or it might be you doing something wrong and then the library returning something that is wrong. Yeah. And in order to figure out what is actually going on in the program, that's where interactive debugging tools come along. And these tools allow you to execute a program in small parts, step by step, or also in larger chunks. And then they allow you to inspect what the program is doing. For instance, programs operate by assigning values to individual memory contents called variables. So you can look up, is this program variable, does it have the right value? Is the program in the current state that I expect it to be? And what if I make use of some third-party function? Does the function give me the result that I expected it to be? So I execute the program under a microscope. So I actually look into what's going on at each individual step, and then I can also halt the program and resume execution just as I like. So that's already a very helpful tool for programmers. The downside is that it's not very automated. So if you have a long execution of, as I said, thousands and millions of lines, figuring out the exact place where to look at and going through things can take a long time.
Yeah. And depending on the language and the framework that somebody's working in, most programmers will have access and will be already using debugging tools. But I think one of the things that often happens, and certainly for a long time when I was new to software engineering, I was really only minimally using interactive debugging tools. So there were lots of capabilities of interactive debugging tools and the IDEs that I was working in that I was barely aware of. So, for instance, something like a conditional breakpoint where the code will stop its execution at a time or in a circumstance that has been determined by you. And I think that maybe one of the first things that you help people with is how to make the most of those interactive debuggers. I know you go a lot further than that. It isn't just about using interactive debuggers, but do you want to talk a little bit about, the maybe underused features of interactive debuggers that people maybe don't make best use of?
One of the least used features of debuggers, yet one of the most powerful, is so-called watch points. So you can specify in a debugger that the program should halt under certain conditions. You already mentioned them. So you can set a breakpoint in the program code, and whenever execution reaches that location in the code, then the execution will stop and will allow you to inspect what's going on. However, you can also set a condition on these breakpoints, and these conditions would be things that you're particularly interested in. Maybe you want to stop the program only when a particular variable has a particular value. Mm-hmm. But there's something that people rarely see, and that's also the ability to check a program continuously whether some variable ever gets a particular value. And these are called watch points, and these are things that conceptually get executed with every line in the program. Yeah. So I can set a watch point on a particular variable, and then I can say, okay, now I'm going to run the program, and whenever this variable, if it ever gets a particular value, then I want my program to stop. I can also make it stop just in case the value of this variable changes. And if this variable, for instance, is an error indicator, then I can set a watch point on this variable, waiting for it to actually get flagged as an error just occurred. Mm-hmm. And if I interrupt the program at this very moment, at the moment the variable gets assigned, then I jump directly into the piece of code that actually makes this happen. Yeah. And this is something that is extremely valuable because it gives me a first idea, where did this value actually come from?
Yeah. And you help people with this, but you are using one particular language for the whole of, for all of your examples. So, obviously you're going to particularly focus on debuggers that people can use with Python, which is your language of choice. And how did you land on Python? Why is Python the chosen language for this book and all of its examples?
Yes. In my book, I wanted to show, I don't necessarily want to come up with dozens and dozens of new debugging tools that are all industry grade. Mm-hmm. That's not my job. Mostly also because turning a program into an industry grade program requires lots and lots of code that is very boring to read and not necessarily interesting for the readers. What I'm interested in is getting the central mechanisms of automated debugging, and making them and implement them, and so that readers can understand how they're working and can either find them in their own tools or can implement them in tools that they build themselves. Yeah. And for this, in order to show off how all these tools work, Python turned out to be a most excellent choice for a number of reasons. Well, first, Python is a language that is very popular. Plenty of people know Python. And if they do not know Python, they can learn Python in an afternoon, even if you come from another programming language. It's not exactly the language that is known to have plenty of huge hurdles for beginners, in particular if you already have an idea of what programming is. Mm-hmm. So this is purely pragmatic. Mm-hmm. The more important thing, however, for my purposes, is that Python is an interpreted language, and which means that you don't compile it with extra compilation steps, but you can execute things directly as they are. Yeah. Which, of course, is helpful if you want to have a book where readers can actually execute the code when they see it. Yeah. Okay, because if you tell them in order to execute this piece of code, you first have to go and put all this extra setup code around it and then compile it and then invoke it as follows. That's horrible. I mean, think of a Java program where in order to do a hello world, you need to do, what is it? Public string, main string, args, system out, print line, hello world. There you have it. Something like that. Okay, yeah. I need to look, every time I want to write a demo example in Java, I need to look this up because I can't remember the right order of things. Yeah. But if for every single example I would have to come up with such a scaffold, okay, this would make things far more complex. And in Python, of course, this is just print. Well, there you go, print 2 plus 2 gives you 4. Yeah. The most important reason, however, is that in Python, it is possible for programs to actually inspect other programs and themselves very easily. So a program can actually, at runtime, check what the individual values of its variables are, and it can also step through through its own execution, as well as through the execution of other programs, of other Python programs, that is. Yeah. Which means that if I want to build an interactive debugger in Python, that is going to take me something like 30, 50 lines of code. Mm-hmm. Okay, and then after 50 lines of code, I have everything I need. I can show off, okay, here's how you step through a program. Here's how you step through a program, and here's how you look at individual variables. Yeah. If I do this in any other language, notably in a language that comes with a compiler, it wouldn't take me 50 lines of code, which is, for me, how long does it take? 2 hours at most. Yeah. It doesn't take me 2 hours. It takes me 2 months. Mm-hmm. Yeah. That's an immense, because then I would have to go through and expand a Java compiler or C compiler with debugging features, or I would have to show how are all these things implemented in a C compiler or Java compiler. Yeah. All of this is horribly complicated because in a compiled language, you have to carry all of this information, this runtime information. How are the individual variable locations? How are they translated into machine code? How can you map back the machine code to the original execution? Yeah. To make all of this possible is a huge engineering effort, which of course, compiler writers do, but they do it once and there you go. Yeah. But in order to illustrate how this works, this is much, much better in an interpreted language, and Python is absolutely great language. If you want to build a toy with debuggers, there's rarely anything better.
Yeah, and I'm really interested in that. I'm going to put a pin in that for now, and then I'm going to return to it later. But let's talk a little bit about the topics that are covered in the book. So one of the things that you talk about is, in the context of debugging, tracking flows and dependencies. So tell me about that and how that relates to debugging.
Yes. The key thing is that when you are debugging a program and you find that at the end the program fails, that's where you typically start. Your program fails because it gets into some state that it is not expected to be, or to return some value that it was not supposed to produce. So the result of your computation is wrong. Okay. So the question is, where does that result come from? Okay. Mm-hmm. And so you have to trace back the steps that particular values come from, which in traditional debugging, notably in debugging with an interactive debugger, is actually fairly difficult because your program executes forwards, whereas your investigation on where individual values come from, this has to go backwards. Yeah? So you have to go back in time in order to figure out, where does this value come from? Does it come from some other value? And every time also you have to check whether the value it comes from is actually valid or not. But this is a classic way of debugging. So you're reasoning backwards and you're following the origins of the value. First, you have a value that is wrong. That's what you start with. That's the very end of the computation. And then you check out its origins, and there you also find an origin that is wrong. And then you check the origins of that origin, and you find another origin that is wrong. And you continue to do so until you find a situation where some inputs are all correct, but the output is wrong. And that's then the one function or the one line of code that did it wrong. That's a typical way of progressing. And as I said, in interactive debugging, that's difficult because your program executes forward. But there's nice tools that allow you to track these dependencies. And the idea here is you go, and every time a variable is assigned a value, you track where the value came from. So you track where the value came from, and you keep this history of all variables until the end of the computation. And so when you're at the end of the computation, it's much easier because you can simply follow the origins. It's like navigating on a map. You can see, okay, this value came from here. Okay, you go to that location. Where did that value come? Oh, it came from there. There you go to that location. And so you can progress much, much quicker in your search than you would normally be able to.
Yeah.
And tracking such information, of course, is somewhat expensive, so it slows down the program. But it's an absolutely great help for debugging.
Yeah.
And that's something I illustrate in the book, how to augment the program execution such that those dependencies and origins are automatically tracked. And then when your program fails, well, you can already be directly pointed to a number of origins where this particular value that is now wrong could possibly have come from.
Yeah. And in that context, you also talk about delta debugging and failure-inducing inputs. Do you want to talk a little about that?
That's another technique. Delta debugging is actually a debugging technique that I am famous for. So I think if there were a Wikipedia entry on me, it would certainly mention me as the inventor of delta debugging.
That's a great thing to have as a claim to fame.
By the way, if there's any readers around, I don't have a Wikipedia entry, so maybe it's time to build one. I cannot do this myself. But delta debugging has one, and it lists me. So delta debugging is another technique for automated debugging. It's also a very powerful one. Delta debugging, here the idea is you have a very long and complex input to your program. Mm-hmm. And if you feed that long and complex input to your program, it fails. Boom.
Yeah.
There you go. And since a long and complex input also means plenty of steps to look at and plenty of memory to examine, this is difficult for programmers to handle. So programmers typically ask you to simplify an input to the largest amount possible, such that it becomes easier for them to debug what's going on.
Yeah.
And delta debugging is a technique that does the simplification automatically, which is the fun. Mm-hmm. So the way it works is it's pretty straightforward, actually. It's a wonder that such a simple technique that fits into something like 20 lines of code actually deserves a name on its own. But, well, I invented it. It works. It works like a charm. And there's a couple of very nice corner cases. But the way it works is as follows. You take the entire input and the program crashes. So far, so good. And then it cuts out parts of the input and sees whether the crash still occurs. Mm-hmm. So it takes out the first quarter. Crash still occurs. Great. Now you just have simplified your input by 1 quarter. It takes out the next quarter, takes out the next quarter, and so on. And the key thing about delta debugging is it starts with by taking out huge chunks of input. Actually, it starts with half of the input first.
Yeah.
And then when it doesn't see any progress, because, well, you cannot simply take away half of an input and expect the input still to work. Well, sometimes you can, but in many cases you can't. And if that doesn't work, and there's the fun in it, then it starts taking out smaller chunks. So it takes out quarters, and then eighths, and then sixteenths. At the very end, it takes out individual characters and see whether this helps. Mm. And it's simply at every time, with every iteration, it checks whether the crash occurs again and again and again. And it keeps on doing that until your input of, well, I've had examples of megabytes being reduced just to individual characters. So it turns out these 10 characters already suffice to bring your program down. Mm. And with this already, programmers, simply by looking at what remains of the input, they already see, hey, it's related to this. Okay, because this is the one single feature that is left in the end. Yeah. And that's already a great help. And then it also helps with... figuring out whether there would be other bugs that actually get reduced to the same input. And this can be extremely helpful. If you find out that, your payment processing fails simply because somebody has an umlaut character or some 8-bit character in their name, mm-hmm. or some weird, UTF-8 encoding, or, hey, how about that? I have a payment to a person who has an emoji in their name. Mm. Something like that, because somebody thought it would be funny to put in an emoji in there, and then everything fails. Well, if your input then if you find out that your program fails whenever there is an emoji and just this emoji in your input, well, you immediately get an idea of where an error came from.
Yeah. So would one example of that be if, for instance, you deliberately created a string that contained all of the characters in a particular character set because you wanted to see whether or not there were any failures, whether there were any problematic characters, then you might find in many contexts, you might find that many of those characters were problematic. So would this technique allow you to identify all of the problematic characters, rather than just one of them, if you see what I mean?
The debugging part comes after you have found a failure. So what you're describing right now is actually a testing technique. But yes, there are testing techniques known as fuzzing that produce plenty of random inputs to a program. And these would then also include, well, what we call nasty inputs, such as, well, emoji or 0 bytes or super long strings or whatsoever. And the typical combination is you first run a fuzzer that produces all these nasty strings, then hopefully finds a couple of situations where your program fails. And then when you have these nasty strings that you know that they fail, then you apply Delta Debugging to figure out what it is in these nasty strings. What is the particular property of these strings that cause a program to fail?
Yeah.
And in the book, Delta Debugging actually comes also with a full-fledged implementation. So this is something that you can actually deploy every day in your program because it does not depend on a particular program code. This is something that you can apply to any program.
Yes. And you also, so that's one of the tools that you share and you share the code for it and you explain how it works. You also share the code for automated software repair. So do you want to talk a little bit about that, about your tool that will automatically repair people's code for them?
Yes, this is a very hot topic in research. So in research and debugging, we are typically not just content with figuring out where the program has a bug or how the bug manifests itself, or for that matter, how we can reproduce a bug with a minimal input or with a minimal number of steps. But what we actually want is we want to suggest a repair to that very code. So this is mostly still a research topic, although there are companies like Facebook, notably, that already have deployed automated repair techniques. And the way this works in practice is you have an automated test that runs every night. And whenever there's a failure, these bug reports then tell you, first, here is a minimal number of steps to reproduce that failure or a minimal input. This comes from Delta Debugging. And second, here is a possible repair for that very bug, a repair that we already found to satisfy all tests. And the way this works is, first, there is Delta Debugging indeed. That's actually a part of that, to reduce inputs to a minimum. Second, there are techniques of so-called fault localization that try to locate potential locations in the code where the bug is. This can, for instance, come from this origin tracking that we found earlier, because if a line of code is not part in the origins, then by construction it cannot have contributed to the failure. And then what automated repair does is it tries to apply random changes to the code, random changes, which at first sight sound horrific. But it also checks these changes on their impact on the failure. So what we do is we try to find changes that fix as many failing bugs as possible, but without touching the passing tests. So we assume there's a test suite with plenty of passing and failing tests, and every single change that we can make that causes one less test to fail without touching the passing test is a potential candidate. And this process can actually take lots of time. So because you have to recompile the code and try again and again. Another advantage of Python, you can just run things without having to recompile them. But in small examples and in specialized environments, this actually works like a charm, and it produces good and sensible repairs. Mm-hmm. It, of course, assumes that you do have a very good test suite that actually is able to catch plenty of bugs. If you do not have that, then the chances are that the repairs are going to fix symptoms rather than causes. Yeah. In practice, many of the fixes look like that. If pointer equals null, then return. That's a fix. Yeah. And this fixes all sorts of pointer errors. But this fixes things with air quotes only, because at the same time, it also removes functionality. Of course, you want your tests to make sure that this functionality is still in there.
That's right. That actually brings us to two topics that are very close to my heart. So two things that I'm very interested in are writing well-factored, easy to understand and easy to maintain code. And another thing that I'm very interested in is test-driven development. But let's start with well-factored code, because I think the first thing that occurs to me, if I'm going to use an automated tool to fix my code for me, that it may well make the tests pass, but will the code still be readable and easy to maintain and understand? So I'm interested in that side of things, if you want to talk a little bit about that.
Fortunately, the tools that we had so far in automated repair produce repairs that are fairly small. Mm-hmm. So we're talking about adding 1-2 lines of code, or coming up with a fix for an off by one error that is introduce a -1, a +1, all that stuff.
Yes.
However, now with the advent of large language models in coding, where you have plenty of AI-generated code, there the sky's the limit for whatever repairs can be produced. And there all of a sudden you have a new risk coming up, because your repair, or the repair suggested by the LLM, which now is no longer small, but which actually suggests, why don't you just replace these 100 lines of code by this other 200 lines of code, which I just hallucinated?
Yes.
Okay. Well, that's another problem.
Yes.
Just 2 days ago, I had to port a rather large, some 200 lines of Python code to C++. And I haven't programmed in C++ for something like 15 years, which is why I simply asked ChatGPT, please do that for me. Translate that. Come on, you can do that. And that worked. And within a second, I had C++ code. Great. And then I used it. And it compiled.
Okay.
Ooh, it compiled.
Impressive.
It just didn't work.
Yeah. Yes.
It just didn't work properly. And then, what can I say? I had to debug this thing. And I spent a whacking 4 hours just debugging what this LLM thing had produced. Yeah. That's all neat. I mean, you can be much luckier than I was, of course, but I thought that, if I had built this code from the very start myself, I would have spent less time.
Yes,
if I had
exactly.
asked an LLM to do that.
I'm hearing that a lot. Yes.
So the future. That's just anecdotal evidence, of course, but. The problem here is, the future of debugging may be more artificial intelligent as it is right now. And that may be a good thing. But I think that for debugging, we have to beef up the abilities of AI to understand code much better than it is today. AI is great, and AI is great in spotting errors in the code that everybody makes. That because this has been fixed in other places and this is discussed in tutorials, and that's where AI is great at. But understanding what's going on in a program, which is what a debugger does, stepping through individual things and figuring out what's going on, that's knowledge you can only have if you really execute the program. And that's not something that you can get by just examining the program code.
Yeah.
So if I had been able to not just give the LLM my little 200 lines of code, but also give it the 20,000 lines of context, and if the LLM had been able to actually execute this and test this, and then finally, maybe a few hours later, come back victorious, including having debugged it itself, sure, I would have been very, very happy.
Yeah.
But we're not there yet. I'm so sorry. So debugging will remain a manual activity for the time being, and our attempts at automating things will make things better, and notably you can go to sleep earlier in the night and come back the next morning with a fresh mind. But for the time being, we'll have to debug things ourselves.
Yeah. So I am interested in the relationship of tests. So you talked about the automated software repair tool requires tests. It needs a good test suite in order to work. And of course, if you've been using the test-driven development paradigm in order to develop your software, then you can be reasonably confident that you will have a good suite of tests. Do you have a kind of ideas about the relationship between test-driven development and the kind of debugging techniques that you recommend?
Yes, clearly, the more you test, and notably the more automated your tests are, the better for debugging. Absolutely. Because for one thing, your tests, of course, well, that's obvious, can help you detecting failures in the first place. If you have a good test suite that comes with plenty of assertions or that simply check for all sorts of things that might go wrong, that's absolutely great. And the more such checks, internal checks you do have in your code, the easier it is for debugging. Mm-hmm. If you come into a function and everything is all right, and at the end of the function something is wrong, well, then you already know that something has gone bad in that function, or at least during its execution, which makes life much easier for any programmer.
Absolutely.
And second, many of the techniques that also we discuss in the debugging book, they depend on a good test suite. Automated repair wants a good test suite. Delta debugging wants automated tests. There's very nice techniques that do statistical correlation between failing tests and specific locations being executed, so-called statistical debugging. This is very common. These also depend on a comprehensive test suite. So the better you test, the easier it is to debug in the end. And since the effort in testing is much more plannable than the effort in debugging.
Yes.
Testing is you just add more and more tests, and you add another test, and you add another test. That's clear progress all along the way.
Yeah.
Debugging, you never know how long it's going to take. There's a risk. I mean, ask the folks in game development when they're being told, well, our big new release is in 4 weeks, and until then we have to fix all the bugs, and then they work in 20-hour shifts in order to squash all of them. Very obviously, that's something you can avoid, but that's where testing and, of course, then test-driven development plays a major role. Yeah,
I'm very happy to hear you say that. So I have one more question, which I think is something that's particularly interesting about this book, because the goal of the book is primarily to help people to debug their software. And you describe a lot of techniques that will help people to debug their software. But you also describe tools such as the automated software repair and the automatic Delta debugging. And you also give the code for those tools so that people could build them themselves or edit them themselves, which in a sense, that's not just about debugging their code. That's building tools to help them debug their code. So rather than just creating a tool yourself and sharing it with people, you're helping them to build those tools and really get into how the tools do the debugging as well as how they will do the debugging. So I'm really interested in the motivation behind that, in why you wanted to actually share the building of the tools as well as the using of the tools, if you see what I mean.
Yep. The answer is very simple. In our education, in our training of programmers, we spent a lot of time on how to build code and how to program. We spent much less time on how to test programs already. We spent extremely little time on how to debug programs, which is a pain because about half of software development goes into debugging, and will be even more with all our LLM-driven vibe coding and whatnot. But you really, really need to understand how to systematically find bugs in your software. And something that is hardly taught at all is actually the usage of modern techniques that help you find bugs automatically. That is, automated debugging tools. And that's the main reason why I wanted to collect these in some executable form, such that students get an idea about what is possible. And, maybe at some point they can invest into open source programs for platforms of their liking. I mean, it doesn't have to be Python. Maybe you want to build a nice Delta debugging tool for C programs or whatnot. So they can invest into that and then make their own debugging easier in the long run.
Yeah.
But yes, that's an investment, and that's going to take time. And unfortunately, I always felt that debugging is like the ugly stepchild of programming. Everybody talks about how they built these beautiful things, but nobody wants to talk about what effort it was to debug them.
Yes.
And people invest a lot into LLM-driven code development and whatnot. But the real thing that eats up time, and that is very, very hard to plan, and that's actually a business risk, is the debugging of code.
Yes.
And that's where, I hope to give some ideas on what we could invest in order to make debugging easier, plannable, and more enjoyable.
Wonderful. And that is a fantastic place to stop. Thank you so much for talking to me, Andreas. It's been wonderful to meet you.
Pleasure was mine. Thank you.
Subscribe to the GOTO YouTube channel now and join the experts in person or online at any upcoming GOTO conference using the promo code Book Club. Visit gotopia.tech to learn more.